So up to this point we've just considered oscillators which are free to oscillate. You know, if I just slightly displace something, it will oscillate naturally as it wishes. But surely you must have considered we can also force something to oscillate. You know, if I keep pushing and shaking something, it will oscillate. I'm making it oscillate. What we've looked at before were free oscillations. That is, where the oscillatory motion of a system, displaced from its equilibrium position, was allowed to oscillate without any external periodic driving forces. And it oscillates just at its natural frequency. You know, the pendulum just ticks naturally. But if I was to hold that pendulum, I could really make it oscillate at any frequency that I wanted, couldn't I? I could just go tick tock, tick tock, tick tock, really upset the clock. That would be a forced oscillation or forced vibration. The motion of the system where there's an external periodic driving force applied and the system is forced to oscillate with a set driving frequency. You get the difference between those two types of oscillation. One of them is just the natural swing of the pendulum, but the other one, I'm kind of taking a hold of it almost and forcing it to tick with whatever frequency I wish. This little book just looks at the difference between those two types of oscillation. What we could also do, if the pendulum was ticking, I could force it to stop, or I could force it to slow down, reduce the amplitude, whatever. If I do the opposite of forcing something to oscillate and I force it to stop oscillating, that is called damping. Those of you that have ever played a musical instrument might be familiar with the idea of damping. If you strum a guitar and then put your hand on it, that is called damping because the sound will stop. So damping is essentially where we apply a force to oppose the motion of the oscillator and stop or reduce the amplitude of the oscillations. Now in the book there are 3 graphs to sketch. Take your time to make sure you get the right one in the right place. Just to clarify, I've come up with this slide. I would like you to sketch the graphs, but I would also like you to write this short description for each type of damping. Light damping is where the amplitude of the oscillator gradually reduces over time. Look at that graph, you can see that the amplitude is slowly getting smaller. This is like in the real world where friction acts on our oscillators. This is like if you were on a swing and suddenly stopped pushing the swing. It would slowly reduce its amplitude until 0. Light damping. If a system is critically damped, then the force has been specifically designed, and we want to reduce the amplitude of those oscillations to 0 as quickly as possible. Now ideally this would go straight from the maximum amplitude to 0, and a good example of this is car suspension. If I went to push down the back of my car, that will be a critically damped system because we don't want to slowly wobble around in our car. That wouldn't be very comfortable. We just want any bounce to be absorbed straight away and we go back to our comfortable sitting position. It might actually be quicker for a critically damped system to oscillate beyond the equilibrium position and back. So we might get a little below and back rather than just going straight to 0. Both are fine. I recommend going with the one that Gary's got sketched in the book here, where it just goes straight to 0. It's the easiest kind. But if you see one where it goes pretty much straight to 0, but it might go below slightly, that could also be a critically damped system. The difference between critically damped and lightly damped is that lightly damped keeps oscillating for ages and it gets smaller and smaller and smaller. Critically damped will go to 0 within the first oscillation or 2. The final is heavy damping. So if you have a look here, like a critically damped system, it goes to 0, but it takes a much longer time. The velocity is actually much reduced by the damping. And a good example of this is the doors in the classrooms at a college. So if you try and slam those doors, they actually have a little mechanism on them that will stop them and then bring them to 0 really gently. So Heavily damped systems, they do go back to zero in the first lot of their oscillation, but they do so very, very slowly. And this might be useful in a situation where you get very rapid oscillations and you want to try and level them out a little bit. You want to try and make sure that the system doesn't respond too quickly. You'll be able to recognise it because it takes a really long time, because the whole of the graph will be committed to slowly reaching zero, whereas in critical damping it will just go boom straight away and there'll still be a lot of graph space left. Take some time to consolidate those. I'll just put that slide up again. Take some time to consolidate those three types of damping. Again, think of some practical use. Well, heavy damping, those classroom doors will not allow you to slam them. They will exert a force against you to make sure they go back to closed slowly and in a controlled way. What about a lightly damped oscillator? Well, in a lightly damped oscillator, it's basically something that's swinging naturally, but with a slight resistive force. So the frequency of that oscillator will be its natural frequency, whatever it would have oscillated with anyway, but the amplitude is what changes over time. Okay, so a quick summary of damping there. What happens if I find something oscillating at its natural frequency, like a pendulum, and I keep pushing it and I give it a little boost periodically at the same frequency? This will be called a resonance. Resonance is where the driving frequency and the natural frequency that it was oscillating with anyway are the same. And in this case, the amplitude just keeps growing and growing and growing. This can be beneficial. I mean, pretty much the whole of music is based on the idea of resonance, for example. And it can also be dangerous, and we'll show you some examples later. Swings. A child on a swing is a really good example of resonance. If you sit on a swing, it does not naturally oscillate. If you displace yourself and then don't kick around, you eventually just go back to the centre point. In order to keep a swing going, you need to provide a periodic driving force by swinging your feet that matches the natural frequency of that system. That's an example of resonance here. The person pushing the swing pushes it at the driving frequency, and when the driving frequency of the person pushing it matches the natural frequency of the swing, the amplitude increases. You need to know about this driving frequency amplitude graph. It's one of the main things that comes up when we discuss resonance and driving forces. I really hope that I'll be able to show you a demo which enables you to almost hear this graph taking place, but alas, I'm at home. The amplitude of the oscillation when there is no force still exists, right? I can set my pendulum going and it will still oscillate, it will still have an amplitude even though I'm not forcing it. But if I were to give it a little push, and the closer I could match that frequency, the larger the amplitude. And what you would see is that if I force my oscillator with a driving frequency the same as its natural frequency, we get a massive, massive, massive increase in amplitude. It's not just a little, oh yeah, bit, it's a huge peak. And then when I stop matching the driving frequency again, when it gets too fast, then it just goes back to normal again, or it stops oscillating altogether. That's how that graph works. It's just showing you that where your driving frequency is the same as your natural frequency, you get a massive spike in amplitude. And that massive spike in amplitude is called a resonance. Resonance only occurs where the driving frequency is the same as the natural frequency. And if I damp a system which is resonating, so if something is oscillating with a maximum amplitude, I provide a small damping force, then the amplitude reduces, that's one thing, but also the natural frequency moves slightly closer to the axis, so it gets slightly smaller. So just looking back to that graph, you'll see a line on it, a little dotted line in the middle. When I damp a system, not only does the peak get smaller, but it gets slightly closer to the origin as well. It moves to the left. Everyone gets 1 mark on a graph question like that for drawing a smaller amplitude, literally everyone, but not everyone gets 2 for moving the frequency slightly to the left, and the peak goes slightly to the left. So keep an eye out for that. We can think of some examples where it causes problems. So the earthquakes, one of the reasons why earthquakes are so damaging is because they cause buildings to resonate. So the earth will oscillate in an earthquake and the buildings will oscillate with it. The earth will force the buildings to resonate at their natural frequency and they'll fall down. Not desirable, and it can be avoided by changing the design of buildings. There are some famous examples of bridges where resonance has caused a problem. There's Victoria Bridge down in London, where there's a sign saying all soldiers must break step as they cross this bridge, because they found that as the soldiers all marched across the bridge in step, the bridge wobbled and they didn't want it to break. The Millennium Bridge between St Paul's and Tate in London is another example of a bridge that had problems with resonance when it was opened. It actually had to close again for about 6 months or something, whilst they fixed the problems with resonance due to people walking with a periodic driving frequency. Resonance isn't always bad, it can be beneficial, and there's some examples. So for example, did you know why microwave ovens heat things up so much? You know, there's a classic, you get GCSE students, as soon as you talk about microwaves, and they instantly say, microwaves are so dangerous. But they're not. You are immersed in a bath of microwaves right now, from Wi-Fi, from the TV, from Bluetooth. You know, microwaves are fine, but why do microwave ovens work? So water molecules have a resonant frequency which is similar to that of a microwave, and so they resonate when you pass microwaves over them and they absorb all that energy as heat. That is a really useful application of resonance. I mean, it is for me because it's how I cook my lunch every day. Another example, I really love this application, is MRI scanners, magnetic resonance imaging scanners. You just need to know that the R in the middle of MRI stands for resonance, and therefore it is a useful application of resonance. Just take it from me, they're very complicated. We can see inside people, so that's pretty handy. You just need to know MR is resonance, and therefore MRI scanners are a useful application of resonance. So to summarise, we normally set this book as a self-study. It's not something we spend a great deal of time going through in lessons other than just talking over what it says. It tells you in the book what resonance is, and you just need to know that standard answer. You just need to know how to draw the graph. You just need to know a few examples of where it's useful and where it's not useful. For damping, you just need to know those 3 different types: light, heavy, critical, and that's it. And you need to kind of just explain why those graphs take the shape that they do and recognise what type it is. It's a small topic, but it features pretty much as maybe a 3 marker on the end of every oscillations question. So normally an oscillations question would feature the bulk of that first book, Oscillations Part 1, and then there'll be a little tag on, or maybe a couple of bits on the end, maybe a Part C, with some questions about forced oscillations and resonance. Again, I really hope that I'll get a chance to show you at some point some examples of resonance and of damping that I don't have to hand today. But I hope it's useful anyway. Take your time to learn the core stuff and spend some time committing those standard answers to memory as well. That's it.